The opinions expressed are those of the participants and do not necessarily reflect the official positions of the sponsors, advertisers, or presenters. Advertising does not imply endorsement by the hosts, guests, and presenters.
I'm a big fan of seeing in the dark. I think that the human visual system has this really, really exquisitely sensitive broad vision system that allows us to even be sensitive to a single photon. And to me, I'm a little saddened by the fact that most humans have this really beautifully evolved system for sensitivity to dim lights that most of us never ever use.
Welcome back to the Restoring Darkness podcast. On today's show, it is our great honor to be joined by Dr. Austin Roorda. After receiving joint PhD degrees in physics and vision science from the University of Waterloo, Dr. Roorda moved south. Over a 30-year academic career, he pioneered the development and use of advanced optical systems for studying human vision in healthy and diseased eyes. He was the first to map the human trichromatic cone mosaic while he was a postdoc at the University of Rochester. He invented the adaptive optic scanning laser ophthalmoscope, I hope I got it right, in his first faculty position at the University of Houston. And over the course of 20 years at the University of California, Berkeley, he developed ways to track eye motion and test human vision in healthy and diseased eyes on a microscopic scale. His latest work involves the use of his OSLO or AOSLO technology to track and stimulate human cone photoreceptors in ways that expand the sensory capabilities of human vision. In July 2025, he returned to Canada to join the faculty at Waterloo. He is a fellow of Optica and Arvo. Notable awards include the Distinguished Alumni Award from the University of Waterloo, the Glenn Fry Award from the American Academy of Optometry, the Guggenheim Fellowship, an Alcon Research Institute Award, the Leverhulme Visiting Professorship from Oxford University, the Rank Prize in Optoelectronics, and the Boynton Award from Optica. We look forward to speaking to him in a minute. But I want to tell you guys really quickly, if you're lighting designers, distributors, specifiers, all that kind of thing out there that listen to this show, environmentalists, there is another option other than LED. So I know it from my career. I've sold many of these fixtures, and they're called magnetic induction lighting. And magnetic induction lighting is a reflected light source. So it uses reflectors to push light in certain directions. And we know that the beam illuminance from LEDs can at least cause discomfort, glare, and Mark Baker would say way more than that. And so magnetic induction lighting is an option for lighting designers to choose from. A great company in that space is called Tesla Induction Lighting Company. And you go to testalightingco.com. And you can check out all their products there, which are great for a host of different outdoor applications. And induction has many of the same characteristics as LED. It's not quite as efficient, but it's really energy efficient. It lasts a really long time, and it works in the cold. So a lot of the things that we like about LEDs, induction has those capabilities as well. So you can go to testalightingco.com and check them out. And also, if you want to donate to the Restoring Darkness podcast, I don't get paid. I'm a volunteer. Mark's a volunteer. Scott gets paid, though, and we have costs. So if you want to throw us $50 or whatever, you can go to restoringdarkness.com, click donate, or you can donate directly to Mark's work at softlights.org by clicking the link there as well. There's a link to Mark Baker if you want to support Soft Lights and some of the truffle hounding Mark Baker's been doing, going into different laws and finding different ways that a lot of this lighting problems we have are already illegal. But we're doing them anyway because we've forgotten about our own regulations. Dr. Roorda, welcome to the Restoring Darkness podcast.
All right. Well, it's a pleasure to be here.
So at the beginning of the show, we were chatting, and you had talked about your color vision research article that had just come out. Tell us a little bit about that.
Yeah. So this was kind of the culmination of about 20 years of research and development that we had done in our lab, but it ultimately led to our ability to not only image cone photoreceptors in a living human eye, but to be able to track and stimulate them. And the cool experiment that we did that got a lot of press in April was the reporting the color experiences that you get when you stimulate only one class of cones. So the retina has three types of cone, sensitive to long, middle, and short wavelengths. They are often called red, green, and blue, but more appropriately long, middle, and short, or L, M, and S. And there's no light in nature. The M cone, the central one, is kind of sandwiched between these two. And all the cones have this broad range of spectral sensitivity, so they all overlap a little bit. So there's no light in nature that can only stimulate the M cone. But in our instrument, we can track the retina, we can see the M cones, we can target individual cones with light, what we call microdoses. We can tickle only the M cones with light in a patch of retina. And when you do that, it sends sensory signals to the brain that are beyond what you've ever experienced. It sends a signal to the brain that's associated with an extreme green color, which is the color that we observed. Um, when we did it, I was a subject. I'm the subject in all my experiments. So I was a subject, and when I experienced, it's a small patch, right? A small patch of light about the size of your fingernail, because of technical constraints. But when we only stimulated the M cones, we got this rich, deep sensation of green that was different from any natural light. So broadly, this falls into line with my interests in research, which is really trying to understand human vision in healthy and diseased eyes on a cellular scale. And this was just one aspect of the kind of research that we do.
You see, there was almost like a sense that other than, so you're seeing a green dot about the size of your fingernail in front of your eye?
Yeah, I
No.
mean, when you're sitting in, we'll call it a display. So it's the
Mhm.
AOSLO display. When you sit in the display, you got this wide um, uh, field of kind of a background neutral gray color. And within that field, there's a square patch that's
Mhm.
about the size of your fingernail, about twice the width of the full moon. And um, when you stimulate only the cones, the M cones in that region, you get this ultra rich, deeply saturated green color.
And you actually see this with your eyes.
Oh yeah, we see it. Right, exactly. I'm just seeing a little patch of super saturated green light.
And then you're creating this by with what instrument? What instrument is used to create that dot?
Well, it's the AOSLO instrument that I described.
Mhm.
So there's a few things you have to do to. I mean, this is a very tricky experiment, right? So there's a few things you have to do to make this happen.
Mhm.
First of all, you have to correct the optics of the eye in order to focus light as sharp, as finely as a single cell. So the technology we use to do that is called adaptive optics. It's a set of tools that measure and compensate for optical imperfections of your cornean lens. So we can compensate for that. So now we can focus light to a spot as small as a single cone. But in a human eye, whenever you're looking at anything, if you're looking at someone's face, reading text on a screen, or looking at a small letter on an acuity chart in an optometrist's office, your eye is constantly moving. Even though you think it is still, even though you
Hmm.
think the world is still, the image is constantly moving across your retina, which is a, it's a natural adaptation of the human visual system, but it makes it difficult for us to stimulate individual cones. So we have other technology within our imaging system that allows us to track the moving retina, see the individual cones in the imaging system, identify which cone is which, and then send little flashes of light into exclusively one class of cones versus the other. So it's an instrument that takes up a 6 foot by 4 foot table in the lab.
And you put your head into this like you're looking into binoculars, or how do you actually engage with it?
Well, the it's very important to keep the eye very well aligned in the system, and so we actually use what's called a bite bar. There's a dental impression plate that I bite into. It's actually bolted into the instrument on an XYZ stage to get your eye perfectly aligned, and you're kind of locked in to the instrument when you're doing. So the head, in effect, becomes a part of the instrument itself.
So, and then as the researcher or the people studying this, they're actually seeing deep into someone's eyes with this technology and looking at the
Yeah,
individual
from
cones.
yeah, from the experimenter standpoint, you are looking at your subject's retina, identifying the cones that you want to stimulate, and then from the subject's perspective, you see this white field of view with a small patch over which those cones are stimulated, and that's the patch that turns this ultra saturated green.
What is it? What are the differences between in this experiment? What are you seeing specifically with the cones when you're looking at diseased eyes versus healthy eyes?
Well, big part of my career has been using this technology. Basically, the technology is a microscope for looking into the eye, and we spent a lot of time and effort using this instrument to look at patients with eye disease and trying to understand how eye disease affects their cells, their cone cells. And then we try to understand how the diseased cone cells function. In other words, right, uh, we try to, we measure uh, the extent to which cone loss affects a patient's visual acuity or light sensitivity, and um, and then we can do experiments to kind of emulate or simulate cone loss to see what are the consequences of losing your cone photoreceptors in various types of eye disease.
Can you observe something like, do they look like they're, rough? Do they look like they're scratched? And then the healthy ones look like, when you see a healthy aquatic animal and their skin is moving like an octopus or something like that, and it looks so healthy. You know what I mean? Is there like a visual difference between the cones that are unhealthy? They look rough or they don't look as, I don't know, moist or something like that. Is there a difference?
Well, we can't look at them that closely. We can see evidence of a cone photoreceptor.
Hmm.
And basically, when we see a healthy cone photoreceptor, it looks like just a bright reflective dot on the
Okay.
retina. So the image of the cone mosaic in a human retina kind of looks like an array of small dots. And in a healthy eye, it's a contiguous, tightly packed array of cells, almost in a hexagonal kind of mosaic, like they would be tiles on the floor.
Hmm.
And in a diseased eye, uh, they can appear in many different ways. So sometimes you'll see a discontinuous array of cones. So instead of seeing a continuous array, there might be cones dropping out, or the cones might look fatter, or uh, or you might get swaths of retina where the cones don't reflect normally. So we spend a lot of time trying to understand how to interpret these images when we look at these patients with eye disease. And the way to interpret it is to try to, in tandem with the imaging, measure their visual function, right? So that's the functional part of it.
How when I've heard, I don't know if this is true or not, and I'm just recalling from memory, but that sometimes some organs can heal, like the liver can heal itself, and it can get better from having liver disease, and then it can come back. What are cones like that? If people have problems with their cones, can they be healed, or once the damage is done, is it permanent?
Yeah, good question. A cone that dies will never come back. The cones that you have when you're born, or maybe shortly after you're born, once you're developed, are the cones you'll have for the rest of your life. So if you lose a cone, it's not like another cone's going to grow and fill in the space. So there are other cell classes in the retina, like skin and certain epithelial layers in the body, where you might regrow cells, but the cones aren't like that. So in my retina, I've been imaging my cones in my retina ever since 2001. And if I take an image of the same patch of retina today, it's exactly the same set of cones. Now, the cone is a very complex cell, right? It's got a nucleus like all cells have, but then it's got this really, really beautiful, the cone the active optical part of the cone is like an optical fiber that aligns in the retina in a special way to receive the light that hits it, um, in order to have it pass through the photosensitive pigment part. Now, there might be parts of the cell that could degenerate or be damaged, and if you don't damage the entire cell, there's a possibility in some cases that parts of the cell that are damaged can regrow. But once a cone is lost, the cone is lost. This is an active area in ophthalmology, because of course many ophthalmologists and scientists are interested in how to regenerate vision in patients with cone loss. Can you revive cones that are sick? Can you put in stem cells to replace cones that have been missing, and things like that?
Wow, that sounds like exciting research. So the you see, you're talking about how this is sending these cones are sending messages to our brain. You said that the cone itself is actually quite a beautiful piece of nature. Like this thing we've evolved, or however you want to talk about how our human eyes got created, whether that's evolution or something different. But we're definitely a good seeing animal, of the animals. The so that cone, if you lose cones, does it make you susceptible to other problems other than vision loss? Like, do people that lose certain cones have different, more likely to suffer depression or something like that?
Well, I think that losing vision will make you more prone to, you know, conditions
Mm.
like suffering from depression, for example. And then on a more scientific side, there are mutations that affect certain cellular processes, and there are mutations that affect vision, but that might also affect hearing, or that might also affect other sensory systems, that maybe the sensory systems that control your balance, like the vestibular system. Um, so the vision loss can occur in hundreds of ways, right? There are hundreds of mutations that cause vision loss, and then there's other light damage, for example, or vascular problems that might ultimately lead to vision loss.
So you mentioned the term light damage, and I think I'm going to ask you maybe one or two more questions, and then I'll turn it over to Mark Baker, because I'm certain I've seen his face and I've seen him watch the show, and he looks like he has a couple of questions for you as well. But you mentioned light damage, and I think what we're interested in whether it's humans or wildlife, um, when we're, so obviously you have the turtle story. The turtle goes the wrong way because he thinks the LED light is the moon. He dies on the road. Okay, the poor little turtle, right? But what we've discovered in this process of going through so many Restoring Darkness podcasts and talking to different researchers and artists and all sorts of different people about this subject is that, what is different about LED light as it interacts with our eyes as opposed to what Mark have consider reflected light sources? So light sources that aren't as sort of laser beamy as LED. Can lighting cause damage to humans? Like, can electric light, like you hear about, you go to a show and it says, be careful if you have sensitivities to strobing lights. You shouldn't watch this show because you might have a seizure. And we have Mark Baker at Soft Lights is thinking that there may be an emerging subset of diseases related to the human eye's exposure to light at night. And we have Dr. Mata talking about how melatonin production can be suppressed. Is there any indications, or do you have a suspicion, or can you speculate, or do you have hard facts to talk about how the human eye will interact with certain kinds of lights and maybe some problems that would be caused by interacting with those kinds of lights?
Well, I'm no expert in this area, except that given that in my lab we are in the business of asking our patients and subjects to stare directly into the laser beam, because the way we form images is by scanning the laser on the retina. And so we have to be very obsessive about safety.
Mm-hmm.
Safety first. We're very, very careful about computing what we think, what we believe, and usually according to the American National Standards Institute, we're very careful in calculating what safe exposure levels are, and we're very careful in constantly measuring and monitoring the exposure levels for our subjects and our patients. And then in terms of the kinds of damage that a subject might experience, well, there are photothermal effects, which basically just involves heating or cooking of the retina in a way. And then there are photochemical effects, which cause chemical changes that can disrupt the physiology of the cell's function, or might lead to byproducts from cell degeneration that are toxic. And the photochemical damage is primarily caused by photons or wavelengths, shorter wavelengths or higher energy photons, or more blue parts of the spectrum. So we think about that a lot, of course, for safety reasons. We don't actively study it. And then the other aspects of light exposure are related to, just as a vision scientist, we think about factors like flicker, right? When a light is strobing or flickering, how sensitive are we to it? Where are we most sensitive to it? What wavelengths are most susceptible to sort of aggravation from flickering lights?
Wow. So you would say that you could hurt people's eyes if you were some kind of evil doctor. You could you could definitely configure your machine to damage people's eyes. Obviously, if with various by stimulating their cones in certain ways, you know that there are areas where damage is caused, and that area is in the blue range of light.
Yeah, that's right. I mean, yeah, we certainly have the capacity to do a lot of damage to the retina. We never have, thankfully.
Yeah.
We never will, for sure, because of the careful control we take. But we are well aware of the hazards. Um, One interesting um, damage phenomenon that I'm quite curious about, given that we are in the business of protecting our subjects and patients, is there is a susceptibility. There are three types of cones, like I said, L, M, and S. S
Yep.
being short. The short wavelength sensitive cone is sensitive to blue light in the spectrum. That seems to be a cell class that's um, particularly sensitive to light damage. Whether it's the cell itself, because morphologically it's a little different type of cell. It acts and looks a little different from the M and the L cell. Whether it's just its structure, or whether it's the blue light exposure itself that causes it. But that's a cell class that's kind of susceptible, more susceptible, I think, than the other two to light damage.
I have two kind of follow-on questions, one or two before I talk about Flickr and throw it over to Mark. Sorry, Mark, but this is really interesting. the is it possible that the lighting industry could create light fixtures? And I'll give you an example with the question. So we know that um, elderly people that are driving at night, I can't remember who I spoke to about this, but that when they drive under a bridge, and if it is overlit or it's lit with this high blue rich or some conditions like that, that their eyesight will fail while driving for a significant period of time when they re-enter the darkness. And so they'll go under this bridge that's lit and they can see, and when they come out the other side, they can't see for 2 or 3 seconds. And the effect happens to everybody, but just some of people's older eyes are unable to make that adjustment while they're driving at 80 kilometers an hour in the States, 60 kilometers, or maybe 75 kilometers an hour, miles per hour on a road in America for American audience. So is it possible that the lighting industry could be inadvertently creating light fixtures that are damaging people's cones or causing problems with the function of the eye? Is that possible that that we've done that?
I mean, I think it's entirely. I think I don't believe that the light exposures would be damaging to the retina, but I certainly believe that this imbalance in illumination, like you described, from a tunnel, you're kind of the opposite. Normally, you think you're in a dark tunnel, and then you have to adapt when you go out into the bright
Mm.
environment. But the opposite occurs when you're in a bright, over-illuminated tunnel and you go into the dark. And the comment you made about elderly experiencing this more, probably two factors that I would surmise um, would be uh, part of that. One is that um, when you get older, your ability to readapt to the dark slows down. And then certain diseases like age-related macular degeneration, one of the hallmarks of that disease is a is a slowing of your ability to recover your dark adapted state. So the ability to see in the dark. So a patient, an elderly individual, or a patient maybe even with early stage macular degeneration would be someone who's most susceptible to the exact situation that you describe. And I'm not surprised that some elderly person would tell you that this is a big problem for them. The other part of it is that as you age, your lens becomes more turbid. In other words, it scatters more light. And this is a well-known phenomena. Everybody with age has a steady increase in scattered light. Um, in And that scattered light is particularly strong toward the blue end of the spectrum. And scattered light when you're driving uh, is can be a serious problem. I mean, although the light may be off to the side, the headlights coming on, or the illumination lights on the ceiling of the tunnel, um, that light, if it scatters, it's not just light from that lamp hitting one part of your retina. It hits your optics and just fills your whole field of view, reducing the contrast of the objects that you're looking at, which might be a pedestrian crossing the street or a street sign or something like that.
Could
So those
something
two factors. Oh, go
no
ahead.
finish up? No, I have. Could that induce a panic attack if that happened to somebody while they were driving, and all of a sudden their vision went? I mean, could someone panic about that and feel like serious mental distress in the moment? Something akin to like a yeah, like panic attack is the only thing I can think of to call that.
I mean, I think I can under certain situations. I mean, it's probably one of the reasons why some elderly folks just will stop driving because they
Hmm.
don't feel comfortable, right? So whether it induces a panic attack is probably, has a lot to do with the individual. I can't think of a physiological reason why a panic attack would ensue, but certainly some individuals would feel very uncomfortable coming out of a lighted tunnel and just say, I can't see. I
Yeah.
don't know where, I don't know where to turn, or I don't feel safe.
Consider induction lighting again. TeslaLightingCo.com. Vis-a-vis the flicker thing, Mark. So one of the things that Mark's really working on right now is the strobing and flickering um, um, lights on our first responder vehicles, and that he Mark, if I'm correct me if I'm wrong here, but he believes that strobing and flickering, obviously it's meant to signal to humans that stay away from this place, but that with the adoption of LED technology into that, the flickering and the strobing is overwhelming for some drivers. Is that something with our cones? And then Mark, I'll turn the show over to you after Dr. Roorda answers that.
Well, I mean, humans are very sensitive to flicker and the kind of uh, flicker rates of some lamps, fluorescent lamps, mini LED lamps generate a flicker that um, can be perceived. And, the humans prefer to see the world uh, continuously. And any kind of flicker disrupts that natural process. So I don't know if you've ever tried playing ping pong with a strobe light illumination, but you literally can't do it. You
Yeah.
can't do it. You need to see the continuous trajectory of the ball to to be able to play properly. And so, and then the perception of flicker uh, varies across the visual field. So, in fact, you're more sensitive to flicker in your peripheral field than you are
Hmm.
along your central vision. And so sometimes you're aware of some flicker in your environment. You look toward it, you go, oh, it's not flickering, and then you turn away and you see it again. And so your vision can kind of play tricks on you that way.
Mark, that can explain the trouble people have with flickering street lights and with police on police vehicles because it's in their periphery that you're seeing it. When you're driving by an LED light and it's flickering, sometimes you can see the flicker. Sometimes you can't visually see it, but you see it when you look at it. I've experienced this myself, Dr. Roorda. So
Mm-hmm.
Mark.
Mm-hmm.
Yeah, and so Dr. Roorda went that ping pong experiment with the strobe light sort of describes the way I react to these police lights or other strobe lights that are flashing lights now, the LEDs. They're so intense, but I feel sort of like I've gone unconscious when they're hitting me. And you sort of described it because I'm only getting sort of partial information. I can't really see my scene anymore because these flashing lights are hitting me. So that, and to tell you, that does throw me into a panic attack. I'm so interested to ask you some technical details. I would like to describe a little bit about my sort of not misunderstanding, but my what I had understood about LED lights initially, and then what I learned recently. So I just came into this field because LED lights impact me a lot, and so I was educated and learned from other people. And one of the things that came out right away was that LEDs, as a flat surface, emit the energies in a Lambertian distribution, so not a homogeneous distribution, not spatially uniform. So this became something that I focused on for several years, that this was kind of the problem with LEDs, that it's this Lambertian spread. But just recently, we had a guest on the show, and he's like, oh, well, that's probably not really the main problem. What you're not realizing is that the human eye has a lens, and this lens, which you study now, focuses the source of the LED light onto your retina and recreates this intensity. And these LEDs have very high luminance. And so maybe the majority of the problem is just the high luminance. Now, I'm in the US, I'm in California. In the US, there's basically zero regulations on luminance or radiance for LEDs. The United States Food and Drug Administration does regulate lasers. And so, as you mentioned, people who work with lasers generally are careful and they're measuring the power of the lasers in radiance. But we don't have that with LEDs. Now, back to my understanding about this Lambertian stuff. So I'd always kind of wondered about measuring the energies at the eye, at the retina. And so, does your research then allow you to measure, well, I guess it would be irradiance at the, are you measuring the irradiance at the cone cell? Or is that calculated some way based upon the radiance? I guess you're using a laser based upon the radiance of the source. How does that work?
Well, I mean, those are all, whenever we do laser safety calculations or do laser exposure measurements, um, we, we do indirectly estimate the retinal irradiance or illuminance,
Oh,
and and of course these take into consideration the spatial extent of the light source. So basically,
yes.
right. So we would measure the power or the irradiance at the surface of the cornea, watts per centimeter squared, for example. Calculate then, given the extent of the object, the illuminator, right, what the size of the image would be on the retina, and then so we can, and making some assumptions about the transmission of the optics, we can then calculate what the watts per centimeter squared is on the retinal surface. And of course, that is the factor, right? The irradiance on the surface of the retina is the factor that governs whether an illuminator is safe or not. And in my view, lasers are well, they're always perceived to be dangerous, but they're very easy to calculate, or easier to calculate retinal irradiance uh, values for, mostly because the property of laser light is well characterized. You can collimate it. You can keep the beam size exactly the way you want it to be. The original source is generally a point source. LEDs get a little more complicated. You have to make some assumptions about their spatial extent. And you're right, they're very compact. So they can, in some situations, they can behave as if they were a point source. And I've done calculations for these types of light sources as well as laser sources, taking these exact factors that I just described to you into consideration. And it is surprising that there's nothing especially dangerous about a laser source, about the photons, except that they can be directed and focused very carefully. And it is a little surprising that the same level of rigor and safety considerations are not so much, like you said, it's a little surprising that they're not being taken into consideration for LED sources. Now they're different, but they can be very powerful light sources and have the capacity to do damage.
Yeah, absolutely. And so I've met with physicists who work in the laser field and talked to them, and they've some of them that I've worked with test lasers and stuff, and they've started to go out into the field and finding people working with LEDs and going, "Holy cow, these LEDs are basically as intense as the lasers, but they don't have any regulations for them. There's something ought to be done." Back to the eye. So, okay, so if I could recap. So you can measure the power at the lens of the eye. You can put a little machine there, I guess. But then you have to,
just a power meter in front of the eye.
Okay.
Oh, sorry. Yeah, go ahead.
No, and so, but then you calculate based upon the lens of the eye, the irradiance landing on the retina. Now, in your experiments with your laser, you can hit one cell, which is just astonishing. You can take that laser and hit one cell, and but an LED is not coherent. LED has a little bit of a spread. LED has actually different distribution of energies across that little spread. So maybe you haven't experimented with an LED, but what would be your theory about, would that light then hit? What I want to know is, like, if the LED light is like whatever 100 watts per centimeter squared at this cell, is it going to be 90 watts per square meter at the next cell over, and 20, 5 cells down the line? You think that's what would be going on?
If I knew the properties of the source and the spatial extent of the source itself, and making some assumptions about the optics of the eye and its focusing ability, I could calculate exactly what you described, what the spatial distribution of light is across the retina. Now, one of the things that we do are very unique, right? Because I can correct for the optics, so I can focus a spot sharper than any natural optics would do. And I can control the eye motion, so I can pin a spot of light onto a ever-moving retina. So if I calculate the light distribution for an LED, one of the ways to mitigate damage, not that we've evolved to do that, but one way to mitigate damage is that the image never remains still on the retinal surface, because the eye is always moving, and so the light, the energy can dissipate a little better as it spreads across a larger area of the retina. But these are all things that we have to think about very carefully when we calculate our retinal irradiance levels and what would be a maximum permissible exposure versus a hazardous one.
So what some of us feel like theorize, we don't have any proof of this, but that the LED, because we have people that have reported to us suffering seizures from an LED streetlight. We don't think it's the flicker because it's instantaneous. So there wasn't really even a chance for flicker. We think it has something to do with the luminance and perhaps this Lambertian spread. So theoretically, had been thinking that, like my understanding is that in daytime, the luminance of some kind of reflected thing, like a rock or a tree or something, is pretty low, like 20 candela per square meter, maybe up to 50 in a bright sunlight or something like that. But that these LEDs as a flat surface source are 100,000, a million candela per square meter. I'm using luminance here, but then so we're not evolved to handle neurological signals where the one M cell is getting one set of energies, and the next M cell is getting a different set of energies, and the R cell is getting a different set of energies. Do you do anything with neurological reactions to the light that you're doing? You did some fascinating things with that green light. Anything with neurology?
No, we don't. No, we're interested in sensitivity to flicker, and but we're not. We've never looked at the neurological aspects of that. But I think that given, I think that LEDs, like a laser, can be characterized sort of objectively quite well. You can measure their spectral properties, spatial properties. Um, you can measure the total irradiance of that source at the level of the eye, and so you could calculate what at least from an objective standpoint, it would not be too difficult to calculate what the retinal distribution of light is.
Excellent.
And
Yeah.
then what happens after that is who knows. But
Okay. Before I turn it over to Michael, I had one other question. One of our supporters is a tetrachromat, if I believe they're called. Have you heard of a tetrachromat, and have you done any experiments with a tetrachromat?
well, we're super interested in that. So great question. Most humans are trichromats. They have three types of cone, right? Short, middle, and long. But there are a lot of polymorphic variations, genetic variations in variations in the genes that encode the cone types and their spectral sensitivities. And many women, so many men have slightly different L cone pigments, for example. Uh, so yours might be slightly different than mine. Mine might peak in its sensitivity to 559 nanometers, and yours might peak in its spectral sensitivity at 563. Okay, subtly different. Now, that's because of the genes that we have that encode our color vision. Now, so these genes exist in the population. Now, women having two X chromosomes can express both versions of those cone types. So instead of having three cone types, they may have a fourth slightly different sensitive L cone pigment. This is just one example of how this can occur. And so it's believed that many women are actually have four cone types. Now, what does it take to become tetrachromatic? That means that can you leverage that fourth cone type to differentiate more spectra than someone that only has three cone types, right? So the way we see color is we use the three cone types, the relative excitations of them, to infer the spectral properties of the world. So color is only a construct of the mind. What is objective in the world is that every object has its own spectrum. And with the three cone types we can differentiate many different spectra. In fact, humans with a mere three cone types, humans can differentiate up to 1 or even 10 million hues, depending on how you measure it. Now, a woman who has a fourth type, can they leverage that extra bit of information to expand the number of spectra that they can differentiate? And There are cases, there are reported cases. There was a really nice, rigorous study done at the University of Cambridge in the UK, where they recruited a lot of known tetrachromats, and many of them didn't exhibit this ability to leverage that fourth type. However, one did, and I say it's a rigorous set of measurements that they did. These were very experienced color vision scientists. The fact that one did means that the brain can use extra information to differentiate colors that a normal trichromat could not. And this is something that fascinates us a lot. Fascinates us a lot. And in fact, testing the extent to which a human can take advantage of a fourth cone type is something that we can do in our apparatus. So we can we can send signals by direct cone stimulation, which is what we use to generate this supersaturated green. We can also send signals to the brain that that is consistent with having a fourth cone type. And we're very interested in the plasticity of the brain and how well, whether or not, if given new sensory input as an adult, can you expand your range of percepts to attribute to them. And it would
Wow.
really mean, here's what it would mean. It would mean you having to invent colors to attribute to spectra that you can't even conceive of now. There's no way you can conceive of these colors, but if you were given a fourth cone type and you wanted to leverage it, you would have to invent new colors.
Sounds like a
Something we're
magical
interested in.
power. It sounds like a
It,
magical power from the X-Men or something.
it is. Now we can only generate these inputs in our system, right? So you would only be able to experience it when you're sitting in a bite bar in a dark room with against a table that's full of optics. But if we showed that you could do that, then it is within the realm of possibilities that one could do a gene therapy to alter the pigments of a subset of cones in their retina to give them this. Now, would you do it? I mean, we don't feel very handicapped by the fact that we have three cone types, do we? I don't think anybody does. Um, so it would the bar would have to be very high in terms of your performance to convince anyone to undergo any kind of treatment like that. Having said that, I'll just finish this argument. There are dichromats, many dichromats, uh, especially in the males. Um, there's anomalous trichromats, which are people that are sort of color deficient, and then there's a less common condition where you only have two cone types. And it similarly to what I had described in a subject who's a pure dichromat, so they're red green colorblind, we could simulate in our system, we could send signals to that person's brain as if they had a third cone type. And one of the big questions we have is, if we did that, would they see colors like a normal trichromatic individual would? And to the extent that they might feel handicapped by their limitations of two cone types, maybe they would be the first candidates for a gene therapy to add a third cone type to their retina.
Wow. That's I always love speaking to the researchers because you always get very precise information. When we talk to
Uh-huh.
the art, we talk to artists and lighting designers. The researchers are always so precise with this is what I know and this is what I'm speculating on, and then I love it. Dr. Roorda, before we go, do you have any final thoughts for this crowd of people that are interested in night preservation and darkness restoration and possibly emerging new conditions that could be caused by exposure to high rich blue light that relate to the eye? Anything like that you want to finish with?
I only have one thought, and it's not related to your specific questions, but I'm a big fan of seeing in the dark. I think that the human visual system has this really, really exquisitely sensitive rod vision system that allows us to even be sensitive to a single photon. And to me, I'm a little saddened by the fact that most humans have this really beautifully evolved system for sensitivity to dim lights that most of us never ever use. It's possible that you've never ever leveraged that capability. It's possible there are people that have never leveraged that capability in their lifetime because they walk around in a dimly lit environment, and you don't really use your visual system to the full extent of its capabilities. It takes about 40 minutes or more, even longer, to fully adapt to the dark. But I'm a big fan of dark adapting and leveraging that capability myself. So I have a property on the Bruce Peninsula, which is in the Great Lakes in Ontario, and it's a very dark region of the world. And I will take every opportunity when I go there to sit outside for an hour or more at night, so that I can see the full, uh, uh, basically the picture in your background, which is of the Milky Way, which is something a lot of people don't really get to experience fully. And one of the reasons why I joined the show, because um, I'm a big fan of dark spaces. Uh,
Hmm. I would also encourage people that, you know, Canadians seem to be very popular in this movement, and I think it's simply because so many of us have had access to wilderness areas in our youth, and when we were growing up, it was very, very common for Canadians to find wilderness, and I don't think it's as common for people in other Western countries as it is for us. Very blessed that way up here, but I would encourage them to even go and experience darkness and have conversations with friends in the dark and let your eyes adjust somewhere where it's dark. And it changes the type of things you talk about, actually. It changes who you are when you experience, exposure to natural darkness and night. It's good. And, I would encourage people to do that. When it comes to, outdoor lighting, Mark, I think that we should tell our friends that and listeners that TeslaLightingCo.com has induction lighting fixtures. Induction is a reflected light source. It's very different from LED, and it can be made in very low Kelvin temperatures, and it can be shielded. It can be controlled. It's instant on and instant off. It has a lot of the great characteristics that people appreciate about LEDs, except it was considered LED's younger sister, ugly sister or something, because it came out in around 2007 or 8. It started to become popular, and then LEDs came along and bulldozed it. But I think it's time, if you're designing lighting systems for outside, to consider induction lighting as a possibility for some of these applications. And you can do that by going to TeslaLightingCo.com. That's TeslaLightingCo.com, and you'll see their wide variety of different induction light fixtures, which again is a reflected light source. It's not a direct light source. And also, if you want to donate to the show, Scott gets paid. Producer's a professional. He gets paid. We have expenses. If you want to donate, that's great. You can go to restoringdarkness.com and click to donate there, or you can even give directly to Mark Baker's work. He's the truffle hound of the lighting industry, digging up all kinds of different laws that already exist and pushing in the courts and trying to get people to answer questions, and we always appreciate that and all of Mark's work. And especially to you, the listener, thank you very much, and bye for now.